Good. So let us briefly recall what regular expressions are. Over an alphabet, sigma. Okay. So this is an inductive definition. So first of all, the empty symbol, the epsilon symbol, any symbol A where A belongs to sigma, these are all regular expressions. And maybe I should write R here. And the language, or the languages they denote, are the empty set, the singleton set containing epsilon, the singleton set containing A, and if R1 and R2 are regular expressions, denoting sets R1 and R2, then R plus S is a regular expression. R followed by S, often we don't bother to write that dot, is a regular expression, and R star is a regular expression, all within parentheses. And again, when there's no confusion, we just drop the parentheses. And the sets they denote are R1 union R2, the concatenation of R and S, and R star. Sorry, it should be R1 and R2. And this, so this is the definition. And then we saw all those examples, but our main goal is to show that this is just another way of presenting regular languages. And to do that, we have to, given a regular expression, we have to come up with an automaton which accepts the same language. And the other way, given an automaton, to come up with a regular expression which denotes the language accepted by the automaton. Okay, so we were looking at one half of this equivalence. If L equals LA, for some DFA, that's a deterministic finite automaton, then there is a regular expression R such that L should use small letters. And we had started the proof. So suppose A had, A is of this form, set of states, alphabet, transition function, and the initial state we'll call Q1. And the set of final states is F, where without any loss of generality, we assume the set Q is of this form, Q1 to Qn. In effect, we are just numbering the states from 1 to n such that the initial state is numbered 1. And then we define a set R. This is a set, and this is parameterized by 3 parameters. The subscripts are R, I, J, and the superscript is K. So what is this? This denotes the set of all strings W which take the automaton A from state Qi to state Qj. Okay, that's why you have I and J in the subscript. And without passing through any state, QL, whose index is greater than K, whose index L is greater than K. This is the crucial definition. Does anyone have any problems with this definition? Any doubts? So if you want to draw a figure, here's Qi, and here's Qj, right? This set Rikj denotes the set of all strings W, which take you from here to there. But there is a further constraint. None of these paths should pass through a state QL where L is greater than K, right? So on all these paths, right, the intermediate states on these paths uh, states have indices less than equal K, right? On all these paths. Yeah. So given this definition, can you now tell me what is the language accepted by A? Suppose F, the set of final states, uh, let me see which notation I'm going to use. The set of final states is, just to be consistent, I'm just checking which notation I have used. Right. Suppose the set of final states is well, you don't even need to do that. But in case you do, suppose it is QJ. No, don't need to do that. Don't need that at all. So can you tell me how to express this in terms of these sets R, I, J, K? Anyone?
IJN.
No, I didn't say that. I didn't specify what the set of final states are. All we know is that the set F is some subset of Q, right? Capital Q. So if Qj belongs to F, right? What can you say about the set of words that are accepted uh, if we reach Qj at the end? What is that set of words? So here's a final state Qj, right? So if we accept by reaching this state Qj, what is that set of words which will lead to that acceptance? Anyone?
Union of Rij star where I belongs to initial states.
We know that Q1 is initial. So if you are going to accept by reaching Qj, right? That would be just by reaching Qj. I'm not talking about the other final states. Suppose there is just one
Is
final state.
R1JN.
Yeah, let us see what the subscript should be. It should definitely be R1J here. But what should be the superscript? I mean, I don't want to place any restriction on the superscript here, right? Do you see that? So what does it mean? I mean, do I really care what is the largest state index on that path? As long as I go from the initial state to the final state, it doesn't, I don't care what indices I pass through. So what should,
N.
that's right. So this should be N, right? Now, this is true only if there is only one final state. But in general, there'll be a number of final states. So you'll have to take the union of all these sets. Remember, this is a set, the set of all words that take you from state Q1 to state Qj without passing through any state numbered greater than n, which means it can pass through any state because n is the greatest index anyway, right? If you take the union over all Qj belonging to F, then you get the language accepted by me, right? Any doubts? Any comments, doubts? So uh, we have made some progress because, as you can see, if we want a regular expression, we just have to replace that union by plus. But then we have to come up with regular expressions that denote these sets RIJL, right? So that's the next thing we do. And this is by induction. Okay. So this is how we do it. Uh, we define R I J K inductively or recursively, if you will, as follows. R I J 0. We have to see what Rij is 0. Okay, that means there's a path in the automaton from state Qi to state Qj without passing through an intermediate state whose index is greater than 0. But all states have index greater than 0, which means there are no intermediate states at all. Okay, so this means this path is either empty, which means I equals j, or there is a single edge from, or a single transition from state Qi to state Qj labeled with that symbol. Okay, so let me just write it down, and let me write it down formally, and then we'll see. So this is the set of all symbols A such that delta Qi A equals Qj if I not equals j. Okay. So when I and j are distinct states, that means there is a single transition labeled with A. So if you collect all those A's into a set, you get the uh, set Rij0. What if I equals j? Then it's possible that there is a transition from the state Qi to Qj itself, because there can be self loops, remember? There can be self loops. So there can be a transition from a state back to itself. And you have to collect all those symbols into a set, union epsilon. If I equals j. Because the empty string will also take you from state I to itself, any state to itself, without passing through any intermediate state. So any doubts about this case? This is the base case. Any doubts? And remember that we are defining a set, right? So Rij0 is a set. It's a set of words or strings, right? So what we have on the right-hand side must be a set. Again, a set of strings, right? And in this particular case, of course, the set of strings is a set containing just one singleton. I mean, strings of length 1 or 0, right? And what is the inductive case? Well, we reason as follows. Remember the definition. This is the set of all words that take you from state Qi to state Qj without passing through any intermediate state whose index is greater than k. So if you look at any such path, there are two cases to consider. Namely, such a path will pass through the highest number state allowed, which is k in this case. So it'll either pass through qk or it'll not pass through qk. So if it doesn't pass through qk, then all these paths will have maximum index k minus 1, right? So all these words which take you from Qi to Qj without passing through Qk, they will form the set Rij k minus 1, because k minus 1 is the maximum possible index, right, of any intermediate state here. On the other hand, that's case one. The case two is when you do pass through the state Qk, and one has to be careful here because the state Qk can be visited a number of times. It's not written anywhere that we must pass through any given state exactly once on any of these paths. That is not the case. So it is possible that we'll loop through Qk a finite number of times and then finally proceed to Qj. And again, on this loop, right? On any of these loops, I'm not suggesting that you must pass through the same loop every time, okay? We'll pass through it a number of times, okay? We may, and on any of these loops, the maximum state index that can appear is again k minus 1. Okay. Because we have accounted for Qk here, right? So to put it down mathematically, this is how we write it. This is Rij k minus 1 union. You go from Qi to Qk, so that's Rik. What should be the index here? At the top? What should I write here?
Zero.
Not 0.
K minus 1.
K minus 1. Right? And then I remain in, I started in Qk and come back to Qk a number of times. So that would be Rkk, k minus 1, right? But then I have to put a star around that. Because I can do that as many times as I want, a finite number of times, of course. And then finally, I'll go from Qk to Qj. And again, the index at the top is k minus 1. Okay. So here, I have an inductive definition of these sets. Okay, and this is the idea of dynamic programming. Okay, because each Rijk is expressed in terms of a value of the superscript, which is lower. In this case, it is k minus 1. So if you see the right-hand side of the equation, we are actually inducting on k, right? So on the right-hand side of the equation, you have only k minus 1 at the top, right? And of course, we know the value for Rij is 0. Therefore, we can fill out the whole table for Rijk, where I and j and k can vary from 1 to, well, k itself will go from 0 to n, but I and j will vary between 1 and n, right? So you can think of it as a table, and we can fill that whole table using this inductive or recursive definition. Okay, in dynamic programming, these are called Bellman-Ford equations. You'll come across these things later in your algorithms course. Okay. Anyway, so is this clear? Right? So we have still not arrived at a regular expression, okay? But that is not difficult once we have defined these sets, because if you look at the definition of Rijk, it uses union, these are really dots here, union, concatenation, and star, okay? And Rij0 is just a finite union of either singleton set of singleton sets, okay? Either symbols in the alphabet or epsilon, right? So from here, arriving at a regular expression is not difficult, right? So let us proceed. So we show that for each I, j, and k, there exists a regular expression which we denote by small r, ijk, which denotes so that denotes the language R ijk by induction on k. So basis, this is k equals 0. We'll actually not write the inductive proof. We'll just show the definition. So in this case, R ij0 is a finite set of strings each of which is either the empty string or a single symbol. How do we get this? From here. Just look at Rij0, right? So there are two cases. In both cases, what Rij0 is, it's a finite union of singleton sets where the element is either a single symbol or epsilon, right? So then we can write Rij0 as A1 plus A2 plus so on plus AP when I not equals J. And Rij, oops, zero is this. Just a set of symbols from the alphabet. So that is the first case, or it'll be A1 plus A2 and so on plus AP plus epsilon when I equals J and Rij0 is all these symbols, contains all these symbols plus epsilon. Okay, so is this part clear? Basically, when I is not equal to J, you just look at all the transitions that can, which are really single edges in the graph, which can take you from state Qi to Qj. And look at the labels of those transitions. And just output the sum of all those. And what if there is no transition from Qi to Qj? What would this sum be? Anyone? Suppose, just to take an example, suppose this is Qi and this is Qj, and there's no transition. From Qi to Qj, right? By transition, I mean a single edge, okay? So for no A, Qj equals delta Qia. In that case, what is our ij0?
Phi.
First of all, just wait a minute. Just wait a minute. First of all, what is capital R I J 0? What is this? And then small. Remember, the top one is a set, and the bottom one is a regular expression. Yes, what is the top one?
Psi.
Don't say psi, you mean something else. Don't even say phi.
Empty set.
Empty set, right? By the way, this is not phi, huh? This is phi. Phi can be written either this way or this way. The empty set symbol is different. It is more like a 0 with a diagonal. And if you know LaTeX, and I'm sure most of you know, there are different symbols for this, right? Okay. And what is Rij? Small Rij?
The symbol for empty set.
Right. This is the same symbol. So that is understood here. The empty sum will be just written this way, right? Yeah. Okay. So that's the basis. And for the regular expression, as I said, the recursive formula for Rijk involves only union concatenation and Kleene closure, that is the Kleene star. So by the induction hypothesis, for each L and M, there exists a recursively, so I'll skip all that. So for Rijk, this is the inductive step. Rijk. This is simply, just look at the definition for capital Rijk and substitute small r for capital R plus for union. Sorry. Rij, sorry, Rik. And this should be k minus 1. K, and this is k minus 1. And the whole thing is starred. And R. So this is the Kleene star here, and R, K, J, K minus 1. Okay. Right. So this is the inductive definition of a regular expression for the set capital Rijk, right? Here's the basis. The basis are the top and the inductive step here. Okay. So this is a valid inductive definition because Rijk is being defined in terms of regular expressions where at the top we have indices less than k. So we have only k minus 1 here, right? And we can go all the way up to 0, and we have defined what it is for k equals 0, right? So because everything in this expression just uses plus and dot and star, what we have is a regular expression. Any doubts? At this point, the usual thing to do is to take an example. And maybe I can try to do that, but I may not be able to finish it in the remaining time. But at least I can show the first few steps, right? So let's take an example. And I'll try to take a very small DFA. So this is the DFA A. Just two states, Q1 and Q2. One is the initial state and Q2 is the only final state. And we're talking about the binary alphabet here. And I won't bother writing the capital R's. I'll straight away go to the regular expressions. So let me do okay. So let me try to do that. So because there are two states, when k is 0, we have to fill out all these things. R110, R120, R210, and R220. Okay. So I'm not writing the regular expressions straight away without going through the sets, right? So can anyone tell me the regular expression R11 for R110?
1 plus epsilon.
That's right. So this is 1 plus epsilon. Right? What is R120?
0 plus epsilon. $210. Empty set symbol.
And 22 is 0 plus 1 plus epsilon. Right? Clear?
Sir, why do we have epsilon in R120?
No. Huh?
Why is there epsilon in R120?
That's incorrect. You're right. From 1 to 2, you can go only on a 0, right? This is, yeah. So, any doubts about this? That is when k is 0. What about k equals 1? Maybe I'll be able to finish this example. It's a race against time. And again, there are, how many cases are there? K equals 1. So there are 4 cases, right? Because each of I and j can be 1 or 2. So there are 4 cases. Sorry. The superscript is 1. Now I am R2, 1. So I have to go back to the automaton. Yeah, here it is. Unfortunately, the screen is pretty small. Anyway, so R111. Well, if you have doubts about what it should be, just go back to the inductive definition. This is the inductive definition. This says how you can express Rijk in terms of Rijk minus 1, right? So I'll just blindly repeat that, right? So what do I get? I have to go from I to j. Without passing through any state with index k, right? Or I can go from I to k and then k back to k. And everything upstairs would be k minus 1. And then from k to j, just put k equals 1 here in this inductive step, and you get this, right? So this would be, I already know these values. R110 is 1 plus epsilon. R110 is 1 plus epsilon. One plus epsilon star, and R110 is 1 plus epsilon. So there'll be a dot here, 1 plus epsilon. Of course, this can be simplified a lot. What you get as a result of this exercise is a horrendous humongous regular expression, but it is a regular expression. Okay. In general, it can be simplified to something much simpler, but we won't go into that. So you know how to do all this now. R121 will be just R120 plus R11. Sorry, this would be, yeah, 0, yeah. And because here K is 1, so R11 0 star, and finally from K to J, R12, right? And so on. So you can expand all that. What is the regular expression for the language? Well, that would be R equals, you have to go from state 1 to state Q, passing through any state, right? So you go from state 1 to state 2, 2. Okay. So you do that, you do this computation using the same strategy, okay? And you'll arrive at it. Okay, so let me stop there. That's the end of today's class. Oh, there'll be